Suppose you drop an apple down a deep well, or off a cliff, or out of an airplane, or some such. Can we figure out how to find height using time? Yes, yes, we can. Okay, I have very carefully measured this point to be exactly 2 meters high. Let's go ahead and see how long it takes for the ball to fall. So we'll go all the way up here. 1, 2, 3.
All right, the general formula for any kind of displacement, if you have time and acceleration, is going to be displacement, or change in position, is equal to v0 times t plus 1 half at squared. Now, our initial velocity, t0, in this particular case, is going to be 0, because we just dropped it. We didn't give it any initial velocity. And that works out to be 1 half at squared, with the a just being our acceleration due to gravity, 9.81. So if we then substitute all of our values, including the 2 meters in our initial displacement, then it works out to be 0.64. Now let's check our work. We initially measured this using our camera to be 0.62. That works out to be a error rate of about 3%, which is pretty good for a cell phone. Okay, at the top we see the formula for the acceleration due to gravity, which in simple terms is the gravitational constant, 6.67 times 10 to the negative 11. And this just simply says how big or small the force is. And this is times the mass of the planet, because the tennis ball was gravitationally attracted to the planet. And the mass of the Earth is 5.97 times 10 to the 24th. And I just looked up the mass of the tennis ball, which is 0.58 kilograms. Remember, everything has to be in kilograms. And the distance between the Earth, the center of the Earth, and the tennis ball is 6.378 times 10 to the 6th squared, and that is also in meters. So I have to be kind of careful with that. So if we plug all of those values in, we get a force of 0.568 newtons. So that is the force that the Earth is exerting on the tennis ball. Now, if we put that number back into our force equation of 0.568 newtons is going to equal the mass of the tennis ball, which is 0.058, then we can solve for the acceleration, which we then get is 9.79, which is different than our kind of standard value. Again, we're just sort of working with what we can on kind of cell phones and stuff like that. So, but if we put that back into our displacement equation, where displacement is equal to 1 half the acceleration times the time squared, we get back our 2 meters, actually fairly precisely, which is, again, pretty good for the experiment that we're doing. Thanks for watching. I hope it was fun.